Welcome. This is the talk after the technology update for this year. This is Alan King with the consortium here. He's going to talk about all the work that he's done with iRODS logical locking for the year. Take it away, Alan.
Okay, thanks, Joe. My name is Alan. I'm one of the what we call core developers on the iRODS team. And as Terrell said, I'll be talking about logical locking. So first, slide. Oh, wow. Okay, my computer's lagging a bit, so apologies if there's some timing issues. The first thing I wanted to address before getting started is, why did this take so long? So you might have been at the user group meetings in years past. In 2019, we presented the idea of intermediate replicas for the first time. That is something we came up with as we were addressing the issues of concurrency that we were seeing from the field. In 2020, intermediate replicas were real, but as that was being developed, we came up with this idea of logical locking, which is, of course, what I'm explaining today. I've linked the slides to our first takes on those concepts in the slides. And so this year, logical locking, or at least write locks, are real. But the reason it took so long is because we had to change everything inside to make it work. This is the internal refactoring that Terrell was talking about, using all the nice libraries that Corey talked about, so that we can have full confidence in what we've been doing with the fewest number of known bugs possible. So this talk is going to be pretty philosophical in nature. There won't be a lot of code to show because this is more of an approach and a concept than anything else. So we are trying to develop a new mental model here. So I'm going to start from the top, some basic stuff that many of you are probably familiar with. So namely, what is a data object and what is a replica? So as stated here, a data object is a logical representation of data that maps to one or more physical instances of a replica, which is an identical physical copy of a data object, which is at rest in a storage resource. On the left is a diagram you may or may not have seen before, which shows a projection of the virtual file system from an iRODS zone. And you've got your data objects up top being projected, or rather being replicated into different servers in your zone. Okay, so now we got replicas and data objects defined. How do we interact with data in iRODS? Specifically, how do we create and modify it? So all data movement in iRODS boils down to three things. And I did talk about this last year as well, so this might look familiar to my slide in the technology update from last year. So first, you open a replica, then you move data to the replica, and then you close the replica. So that's all it boils down to at the lowest levels. And iRODS supports a POSIX-like interface for opening, writing, and closing, which are exposed via a few API endpoints. But what many of you are probably more familiar with are these higher level APIs that map directly to many of the I commands you might use every day. So puts, copies, replications, phi moves, whatever. And these are now built using these lower level APIs. So again, all data movement is opening the replica, moving the data, and then closing the replica. I finally wanted to mention this idea of policy being invoked, which can result in data modifying operations. And that is an important concept to keep in mind as we talk about concurrency within our system. So just a few more terms here. So I'm going to use the word truth to refer to how the data should be. More formally, it is the latest data known to be correct. So the last thing you put in that is correctly transferred is the truth. We represent this with a replica status in the catalog, and that is the state of the data as it relates to physical storage and the catalog and the truth. So when we talk about replica statuses in the past, there have only been two. And what do we mean by that? So a good replica is data that is at rest, it matches what's in the catalog, and it reflects the truth. A stale replica is data that is at rest, but it does not meet all of the criteria for being good, meaning it may not match what's in the catalog, or it may not reflect the truth. If it's not reflecting what's in the catalog, there may have been data transfer errors, there might be a mismatched checksum, some sort of corruption on disk, who knows, anything that would cause it to not match the catalog, or it doesn't reflect the truth, which could mean either the catalog is now showing something that is not true of the data in storage, or more recently written data has been created, and that is now the new truth because it's more recently written. I wanted to note that this does not mean that stale replicas are necessarily incorrect. It just means that they are no longer the latest reflection of how the data should be. So there's no way outside of some sort of monitoring service that we can know that it is reflecting the truth. All right. So there are three problems we identified when thinking about locking. So why are we even talking about locking? And the answer is concurrency in a distributed system. It is almost inherent if you have a distributed system that there will be concurrency. So there are three problems we identified. First being data corruption. If there's uncoordinated concurrent writing to a single replica, your data can end up in a state that is not good. If there's uncoordinated concurrent writing to multiple replicas of the same data object, you have what I'm going to refer to as truth corruption. So you don't know what the truth is at that point because it's a race condition based on who finishes writing and finalizing the catalog last. And there's no coordination between the agents that are writing, so we don't know. Finally, wanted to talk about uncoordinated concurrent high-level operation execution as a result of policy can lead to policy violations. So this might look like I wanted 2 replicas instead of 3, but multiple concurrent agents are coming in and performing hierarchy resolutions or voting, as you might know it, and coming up with different results, which leads to concurrent replications, which leads to extra replicas, as an example. So all 3 of these problems endanger our understanding of the state of the data, which is how we know that our data is stored and cataloged safely and correctly. This kind of goes back to what Pete was talking about this morning. Consistency is really, really important as far as cataloging your data. So I just wanted to show a little sequence diagram about how an iput works to kind of give an idea of what goes on there. I promise it's not random. So going from the left, we've got a client that, say, does an RC data OJ put. This then is redirected to the catalog service provider to register this replica in the catalog. Then we redirect to the place where the data is going with the file open. If it's a large enough file, and I guess historically we have set up a separate portal on the high ports. So we set up the portal, transfer information, it's returned to the client who then connects loops using parallel transfer to directly transfer data to the storage host via a direct connection. Once it's completed, we call close, which then closes up the file and finalizes the state in the catalog, which marks it good or stale, depending on, or updates checksums and sizes and whatnot, depending on how the data transfer went. Now, I put all of this in a big box and marked it as a critical section. That's because this whole time, any other, at least historically, any other agent could come along and open up this same replica and start writing to it without the original agent knowing any better, and you end up with potentially data that you did not expect. So this leads us to our first problem of data corruption. Our answer to this, as highlighted last year and the year before, was intermediate replicas. So again, the problem is that we have in-flight replicas that can be opened and modified in an uncoordinated fashion by multiple agents. And then the catalog may not reflect the current true state of the replica. So the solution is to introduce a new replica status. So we had good and stale, which I described before. Now we have intermediate to show that a replica is in flight or that it's actively being written to. In this way, we show we accurately represent the state of the data in the catalog, and then the system and users can take appropriate action based on whether or not the data is at rest. This leads to our next problem of truth corruption. So if you have, if you have multiple replicas for a data object, which is probably a best practice, I can't speak on that, I'm not a policy writer, you may want to know which of those replicas is representing the truth. If all is well and good, all of them are representing the truth. But if you have multiple replicas and multiple agents come along and update those different replicas at the same time, it's unclear where the truth now lives. So logical locking, in addition to the intermediate state for the actual replica being updated, now locks down all of the other replicas so that they can't be opened for read or write, so that expectations are maintained as far as the correctness of the data going in and out. So to kind of quickly go over what that looks like, if you've got a replica which is actively being written, and then another replica that an agent comes along and wants to read, we can't guarantee that that replica any longer is what you expect. It may not be the data as it should be, may not be the truth. So that is why we have gone along and implemented logical locking in this way. So I'm intentionally avoiding going into too many implementation details to kind of keep this talk short, but I'm happy to talk about that. I did want to go over a number of limitations and trade-offs as it is currently implemented, that is, as logical locking is currently implemented. So as I mentioned before, in 429, the write lock is what has been implemented so far. And what this does is introduce a trade-off in time. So now we have to hit the catalog up to 3 times just to make sure that the information is correct for a given data object on a create, and 2 times for a write. So you have to lock the object, register the new replica, or close and finalize. And then for write, you have to lock the object and close and finalize. So in the past, all you had to do was register the new replica and then finalize it for a create. And for a write, all you had to do was close and finalize it because it just maintained whatever state it was in at the time of opening. But then you don't know that that replica is in flight across the system. The other trade-off that we had to make a decision about was the space trade-off. So as you as you maintain the states of all the replicas in the system that are in flight, you have to keep it all in memory. We're also writing down more things in the catalog, so there is a bit of a space trade-off there. As well, I wanted to address 2 things that logical locking does not solve. Database race conditions, that is, if 2 agents show up at the exact same time trying to write to the exact same replica, one of them is going to win the race and lock the object down first. And we have no way of really knowing when that's going to happen because iRODS is not psychic. And we do not protect against rogue administrators, which should be obvious. Finally, as currently implemented, logical locking is scoped on open and close and not by operation. So that leads into the third problem that I brought up before, and kind of a nice transition into the future of logical locking. So here's another example. So we've zoomed out a bit. This box here inside the big box is kind of what we were seeing before, in a more zoomed out fashion. So let's say you do a put to a replication resource hierarchy. So the initial replica is created, everything goes great, it's finalized in the catalog, and then there's something called file modified. This is effectively a way of signaling to the resources that something has changed inside of the hierarchy as far as the data goes, and they can take the appropriate action based on the encoded policy in those coordinating resources. So in the case of a replication resource, we have replication. So this could trigger, multiple REPLs, which I've placed in boxes here. Now, each of these is enclosed in a box and marked as a critical section. That is, we have to lock those down and make sure that no other agents can come in and open this object while we are writing to one of the replicas in order to maintain the truth. But as currently implemented, you can see there's gaps in between for this particular operation. So we gate it on open and close. So in put, we lock down the object, then we unlock, then we replicate, locking the object, then we unlock, then we do the next replication, then we unlock. So what we'd like to do in the future is make this big box true. So this whole thing is a critical section as far as your policy goes. This is where policy violations come in. It's what I'm calling operation locking. We're still working on that name, so open suggestions there. So first, if a data modifying operation is impacted by policy, which leads to other data modifying operations, and you get concurrent uncoordinated data modifying operations going at the same time, this may lead to violations in your policy, which is what I described before. So what we'd like to do for the near future, is to keep the data object locked over the lifetime of the entire operation. So this would make put more aware of logical locking rather than being dumb and just calling open and close and expecting the lock to be acquired. This would also require that our locking be more self-aware about who's holding locks, and that leads into the next point. We have read locks planned for the future. So if an agent is currently reading an object, modifying or unlinking said object while it is being read is obviously a problem. So we would like to extend iRODS logical locking to allow for multi-reader single writer access, which is a well-known pattern in CompSci world. I've put a few implementation details down here for this as far as our planned approach. So of note is this list of agents and host names, which are holding locks, which will be known across the system so that we can do things like be self-aware about, oh, I'm the one holding the lock, so we don't get into deadlock situations when we implement our policy, our operation locking. Finally, I wanted to highlight another thing that we are planning on doing using the asynchronous tasks module or tool or agent, I don't know what we're calling it, being written by one of our interns this summer. We'd love to be able to implement a lock checker. So as mentioned before, agents holding the open descriptors are responsible for locking and unlocking objects. If an agent is killed for whatever reason, that can leave objects stuck in locked or intermediate state, and admins have to identify and modify the state so that they can be healed. That's not great. So we'd love to use this asynchronous server task to identify which locks are being held open and if that agent is still alive. So it can ping the server, which is holding a lock as noted before. And then we can see if that agent is still alive. And if it's not, then we can go ahead and unlock that object so that it can be accessed again in the system. So that's all I've got. Thanks for listening.
Very good, very good. Thank you, Alan. Do we have any question? Let me go read some things. We do have a question about when iRODS 4.3 is going to be released. Do you have an answer for that, Alan?
I would love for that to happen before UGM 2022, but I'm not the one making those shot calls, so.
Fine answer. Fine answer. We do have, I think, lots of people who don't know what to ask you about all this, just because it's deep. But I do believe that it builds a lot of confidence. And yes, we put Alan in the cave for, was it about 2.5 years, I think?
I think, yeah, intermediates started maybe 6 months before UGM 2019. So
right.
Yeah.
And then two full years as we kept pulling on things and consolidating code paths, new surprising edge cases would show up. But a lot of this really was driven by the workflow at Sanger.
Mm-hmm.
They have a tremendous number of parallel and concurrent operations, and sometimes for robustness, they're overriding the same logical path. And so we were in contact with them a lot, and I'm hoping, we're very excited to finally see some of their pipelines and stuff on this new code, because I think that some of their things will be cleaned up quite a bit.
Right. In my theoretical example about 2 replicas versus 3 is a direct problem that they were seeing,
right.
well, are seeing in their production deployment.
One thing that you talked about, the number of hits to the database, do we think it's possible that in the create case, the create and the registration can happen at the same time, and then we get it down to 2 potentially?
A create and a registration can happen at the same time.
In the if you go back a few slides with the locking, yeah, you talked about three hits to the database for the lock in the create case. Up here, yeah, the top.
So the idea here is that you have to lock down your object so that multiple agents can't come along. What I found is that when I was doing a create of a new replica of an existing data object, you have to make sure your object is locked so that you can't have 2 things creating and then locking, if that makes sense.
Right.
We could ostensibly introduce a new API plugin which does all this at the same time, but this is using existing machinery for the, since it's been battle tested for many years. So a lot of that stuff is just in the existing machinery.
Yeah, we do have an API plugin in the works for atomic operations, and so this might be.
Oh, sure, absolutely.
Okay. Let's see. We've got one more question from the French National Library. It says, does it mean writing replicas is serialized inside of a replication resource?
Yes, so that is something that actually came as a surprise to a few of our team members as well. The replication resource does synchronous replication as a result of the file modified operation. So you don't get your prompt back on the client side, which I neglected to draw an arrow back until all of the replication is done. We do plan, I believe, in the future, perhaps a 4.3, to allow for asynchronous replications to be scheduled as a result, but we wouldn't be able to wrap locking around that due to the asynchronous nature.
Right, so we could either offer for an asynchronous, we can already do that. That's already an option. The other thing would be to actually make the replications concurrent and just have a block. That they wouldn't be serialized.
I did neglect to mention that in this talk. Yes, we would love to do parallel synchronous replication as well in the future, using the replica access table as a way of coordinating the writes.
That's right, but yeah, that's not how it works now, and it has never done that way. It's always been a serialized replication to all children of the replication resource.
And this would also allow rebalance to run that way as well.
That's correct. Yeah, rebalance. The rebalance iadmin command is also extremely serial in one sense because we knew it was going to be run in the background already. And two, hopefully, if this is a regular thing, you don't have too many things out of balance. But also it means that reporting those results are much easier because it's very hard to communicate a partial failure or partial success in a way that is sane to the administrator. So yeah, the rebalance is going to require a little bit more thinking to make that cleanly concurrent, but that is something that we look to do in the future. Is iMove still supported?
iMove is still supported. That is a pure database operation. However, you cannot move something that is locked because concurrency.
Correct. So yeah, move does rename the physical replicas by default if your policy is to keep your naming clean and consistent. But it doesn't move.
Oh, that's true.
It doesn't change them from resource to resource. So it's just an OS rename as well. And then last question here says replica paths would follow the data object path, right? So yes, it would still rename on the physical layer as well, but
yes,
that's not a time-consuming operation in most systems. Very good. I think we have. Oh, they're still coming, Alan.
Oh boy.
Very interesting. There will be new ICAT object attributes for logical locking to make query with the status of the replicas. So I think the answer to that is it's captured in the replica status. Can you go back to the ampersand and question mark? And
so I actually opted to exclude that slide this time around, just because I didn't feel that it was super helpful in this particular talk, but the replica status is captured in the data is dirty column in our data main, if you want to get into the nitty gritty. So that has historically been a good or stale, so 0 or 1. Sorry, 1 or 0 respectively. And we have added 2 new replica statuses. So instead of just 0, 1, we now have 2 and 3 for intermediate and write lock respectively. And then for maintaining our agent list, there is an unused column called data status, which we are writing down things like the original replica status so that we can restore that status after a thing has been locked. And then we are going to expand that to also include this agent PID list and whatever else we need. So no database changes needed is the short answer.
right. And so
if that was the question.
Yeah, and so in terms of being able to query those types of things, yes, those columns are already available via iRODS or genquery. So instead of looking for a 0 or a 1 to do the logic that you might care about, you could just look for a 2 or a 3 if that was interesting to you. So I hope, Mustafa, that answers your question. I think we're slowing down. All right, I think we did it. Thank you, Alan.
Thanks.